All right, today we're diving into something that feels like a genuine cosmic whodunit. It's a mystery playing out at the very limits of what we know about physics, and it involves a new theory so radical it could completely change how we think about, well, everything.
So, here's the central puzzle. When we look out into space, we see things like exploding stars and black holes acting like giant particle accelerators, flinging particles at incredible energies. And you'd think we'd see a whole range of them, getting faster and faster. But that's not what happens. At the very highest energies, it's like they hit some kind of invisible wall. They just vanish. So the big question is, where did they all go?
Okay, so here's what's so weird about it. On the one hand, our standard physics predicts that we should see this nice, smooth curve of cosmic ray energies, but when we actually point our telescopes at the sky, nope. What we see instead is this really sharp, sudden drop-off. Physicists have a nickname for it. They call it the cosmic ray knee. And for decades, nobody's had a really good explanation for why it's there. It's a huge puzzle.
Now, to crack this puzzle, some physicists are proposing something, well, pretty out there. They're asking us to toss out one of our most basic assumptions about the universe. What if space isn't this smooth, continuous analog thing? What if it's digital? What if reality itself is built on a kind of grid, like a giant cosmic network with its own rules and, crucially, its own limits? Now, if you're going to have a network, you need hardware, right? Basic components. While in this model, the first piece is the pixel of reality. Think of it like the pixels on your screen. There's a smallest possible dot. In the universe, that's called the Planck grain. It is the absolute rock-bottom resolution of reality itself. You literally can't zoom in any further than that. And just like your monitor has a refresh rate, this cosmic network does too. It's called the Planck frequency, and the speed is just mind-boggling. We're talking about 10 with 43 zeros after it, updates per second. That's how fast the network of reality processes change. That's the refresh rate of the universe. This whole idea even changes how we see one of Einstein's biggest contributions, Lorentz invariance. All that really means is that the laws of physics are the same for everybody no matter how they're moving. But in this digital universe model, it's not some grand mystical law. It's more like a network protocol, like TCP/IP for the internet. It's just the rule that makes sure a particle hands off properly from one pixel to the next. As long as that digital handshake goes smoothly, everything looks normal. And this is where it gets really, really interesting. Because think about it. Every network has limits, right? Your home Wi-Fi can only handle so much data. The internet has a certain bandwidth. So, what are the limitations of the universe's network? What happens when you try to push it too hard, right to its absolute limit? Well, according to this theory, the cosmic network can fail in two distinct ways. First, there's a structural limit. Basically, how much mass can you cram into one spot before you literally break a pixel of space? And second, and this is the one we really care about for our mystery, there's a bandwidth limit. How much kinetic energy can a particle have before the universe's refresh rate just can't keep up with it anymore? So that bandwidth limit, that's our smoking gun. The theory says that the cosmic ray knee, that big, mysterious drop-off we started with, it's not something weird happening out there with stars or galaxies. No. It is the signature of the universe itself telling us, sorry, that's all the bandwidth I've got.
Now, here's the really cool part. This isn't just some hand-wavy idea. The theory actually provides a specific formula to calculate this limit. And get this, it's derived from just two fundamental constants of nature. You can think of them as the technical specs of the network. You plug those two values in, you do the math, and it spits out a very specific number. And that number is 4.86 peta-electron volts, or PeV. Now, just to give you some perspective, that's an insane amount of energy, hundreds of times more powerful than anything we can create at the Large Hadron Collider. This theory says that 4.86 PeV is the universe's ultimate energy limit for a fundamental particle. So remember that number, 4.86. Okay, so remember our big mystery, the cosmic ray knee? Well, all of our observational data shows that the drop-off happens somewhere in the range of 3 to 5 PeV. And what did our new theory just predict? 4.86 PeV. That's not just close, that is a direct hit smack in the middle of the observed range. And remember, this wasn't a guess. The theory calculated this number from first principles, and it just happens to match what we actually see in the sky. Wow. So what's actually happening at that limit? The theory calls it vacuum aliasing. Now, if you've ever worked with digital audio or video, you probably know what aliasing is. If your signal is changing faster than your sample rate, you get all sorts of weird artifacts and distortion. It's the exact same idea here. The particle has so much energy, it's essentially moving too fast for the universe's sample rate. So it starts to skip pixels, and every time it does, it sheds energy. The universe itself is literally putting the brakes on it.
Okay, but it can't be that simple, right? There's always a catch. And the big critique of this idea is pretty compelling. It's known as the iron nucleus paradox. The basic question is, if this is a fundamental limit of space itself, shouldn't it be the exact same for every particle?
And here's the problem for the theory. When astronomers look out there, they see that heavier particles, like an iron nucleus, seem to reach their knee at a much, much higher total energy than a simple proton does. That really looks like the limit is tied to the particle itself, not the vacuum of space. And honestly, that sounds like a total deal breaker for this whole digital universe idea. But stick with me here. Because the theory has this incredibly elegant comeback. It says, you're right, but you're looking at it the wrong way. That 4.86 PeV limit isn't for the whole particle. It's for each individual building block inside it, each proton and neutron. A proton? Well, that's just one block, so its limit is 4.86 PeV, just like we said. But an iron nucleus? That's a bundle of 56 of those blocks all stuck together. So the entire nucleus can carry 56 times that energy before any one of its components hits the cosmic speed limit. And just like that, what looked like a fatal flaw suddenly becomes maybe the strongest evidence for the theory. It just clicks right into place. You know, a really great scientific theory doesn't just explain old mysteries. It makes bold new predictions that you can actually go out and test. And this one has another huge one. Remember that other limit we talked about a minute ago? That structural limit on mass? Well, when you run the numbers for that, the theory predicts that there is an absolute maximum mass for any single elementary particle. And that mass is 35.5 tera-electron volts. The theory claims you just can't have a fundamental particle that's heavier than that. It's impossible. Why? Because the very network of space itself would literally tear apart. And that's what makes this real science. It gives us two very clear ways to prove it wrong. It's basically a challenge. It says, go ahead, build a bigger particle collider and find a fundamental particle with a mass over 35.5 TeV. If you do, our theory's busted. Or point your telescopes up and find a single proton zipping along just fine, way above that 4.86 PeV limit. If you see that, we're wrong. A good theory isn't afraid to be wrong. It puts its predictions right out there on the table. So, in the end, it all comes down to this really profound question. Are the ultimate rules of our universe written in the language of physics as we've always understood it? Things like matter, energy, and forces. Or are they written in the language of information theory? Pixels, refresh rates, and bandwidth? Is reality truly analog, or is the universe at its deepest, most fundamental level digital? That's a pretty wild thought to end on.